These two terms you would have often come across when you're studying convolutional neural network. The convolution is used in various other places as well. I'm going to talk in this session about these two concepts, convolution and pooling. It will be in the context of image processing using CNN. The reason why I chose this topic is often beginners in this particular topic come to me and ask me about convolution and pooling after going through the way these two different techniques are explained in the various books and articles. So I thought, why not share the way I understood convolution and pooling in the context of CNN used for image processing. So welcome to this session on Introduction to Convolution and Pooling. By no way is this going to be an end-to-end introduction to convolutional neural network. That is not the objective. The objective is get the concepts of these two terms, behind these two terms into place. So formally, I welcome you all to this session, and whatever questions you have, feel free to put it on the chat, and whatever number of questions I'm able to take in this session, I will take. So I'm going to begin with introducing you to the landscape that we're going to cover today. I'm going to talk about digital images and pixels, because this is very important when you're talking about convolution. You need to understand certain things about digital. For instance, you cannot do convolutional neural network based modeling on analog images that you used to come across when we used reels way back in the 70s. All these technologies need the input to be digitized of the digitized form. So we need to know something about digital images. Then the process of capturing this digital image, we all know how we do it. We use our digital cameras in our phones or SLRs, but still there are certain other things that you need to know beyond these different ways of capturing digital images. And with these concepts in place, we'll be ready to go and explore what convolution is and what pooling is. So when we're discussing these two, I'll take you through convolution process. What does it mean? Then we'll come across terms like kernels and filters and feature maps. Similarly, when we're doing pooling, I'll take you through the two very important things that you should know, that is max pooling and average pooling. What do these things stand for, and how do we use them in CNN? So let me start by giving you an introduction to convolution first. And for that, as I said, we first need to understand digital images. Many of you would have seen these kind of pictures in various books, articles, online when they discuss convolution. In this, they show you a grid of numbers. They show a smaller grid of numbers, and there is some process whereby this smaller grid, it scans this entire grid and gives you an output, which is shown over here. So let me start from the beginning. You have a larger grid of numbers, and then you have the smaller grid of numbers, which is placed on the larger grid, edge to edge. These are called the weights multiplied by these numbers, and the result of that is simple linear weighted addition. In this case is 5. How do you get 5? When you ask this question, what they would be telling you is 1 into 1 plus 2 into 0 plus 1 into 1, the first row. Similarly, 2 into 0 plus 0 into 1 plus 0 into 0, and so on and so forth. And total this up, you get 5. Then you shift this smaller grid onto the next part of the larger grid and do the same operation. This is what they will show you as convolution in many of these books and articles that you come across. And this leaves you wondering, what is this grid of numbers? What do these numbers represent? Similarly, what are these numbers? What does the smaller grid represent? And what is this output that you're getting over here? What are these numbers? These questions, unfortunately, remain unanswered. In fact, some people go to say that this is a way of extracting information from the images. And that leaves the students with a lot of questions, more questions than answers. So my objective is to explain to you what exactly is going on here. And what is this process called convolution? And what does it result in? So let's move on. As I said, to understand this process of convolution, we first need to understand what digital images are. A brief introduction to this digital image. Digital images are also known as 2D discrete space. The reason why they're called 2D is they have two dimensions. Discrete space, the word discrete means in this space or in this area, you have information stored in this area in discrete numbers, whole numbers. You cannot have fractions there. You cannot have negative numbers there. These are whole numbers. They're positives. You can call them positive integers. And they lie within certain range, 0 to 255. That's why it's called discrete space. To generate this digital image, you use a device which is a camera. That camera converts the analog information in front of you. Maybe you're standing in front of a beautiful scenario and you're capturing an image through your camera. You're converting the analog information into digital information. The 2D analog space is represented by this 2D analog space is represented by this 2D digital image, where the digital image consists of what we call pixels, which I have shown here as these cells, but these are not truly pixels for the time being. You please imagine them to be pixels. So we convert the real world, which is an analog world, into a digital world. This digital world consists of two-dimensional image made of pixels. What is a pixel? Pixel is the smallest unit of information in that picture. We'll see more of pixel down the line. What value these pixels acquire depends on how much light is coming from this analog real world into your camera through the lens. This process of converting the reality, which is an analog field, into a discrete space, which is a digital field, this is called amplitude quantization. We really don't need to worry too much about this amplitude quantization, but often people use these terms explaining this digital image. So that's why I'm introducing you into this concept of amplitude quantization. What you need to understand is a digital image is a sample of the real world. It's like sampling from the universe. That sample is when the shutter of the device opens and shuts. During that time, whatever information comes into your device and gets converted into image, that is called amplitude quantization. All right, so what? We have to look at the same digital image. We have to look at this digital image from another perspective. And this perspective is you have to look at it as a function to understand convolution. What do you mean by image as a function? I've taken this 2D image. This is a grayscale image. It doesn't have colors. It has shades of gray from the SK image library. It's called the cameraman. You can take any image you like. Let's look at this image in a different angle, which is called the isometric view. The reason I'm doing this is to explain the concepts below. Now what I'm going to do is I'm going to plot. There are two axes here, x1, x2. I'm going to plot a third, which is perpendicular to these two axes. That axis will represent pixel intensities. So in any grayscale image, the pixel intensities can range from 0 to 255. 0 means absolutely black. 25 means absolutely white. So if I look at the image, if I open this image file and look at the raw data in it, you might find 255 in these positions and 0 in all these positions. So the lesser the value of pixel intensity, the more black it is. The larger the pixel intensity, the more white it is. And the pixel intensity is 0 for black, 255 for white. Now the same 0 to 255 apply for red, green, blue, the three different channels which make all the different colors that we see. In this example, I've taken grayscale image, and the same 0 to 255 scale is applicable to grayscale image as well. So now let's go ahead and plot. In third dimension, the intensities of these pixels which make this image. And when you do that, this is what you get. The vertical axis y is pixel intensity, and if you look at it, the maximum pixel intensity it can have is 255. Lowest one it can have is a 0. So what you're seeing here is pixel intensities at various positions on this input image. This input image, if you can think of it as the base of this chart, what you're seeing here is these pixels have a very high pixel intensity value, almost close to, say, 200, because they are light in color, almost close to white. These pixels, which you see on the base, on the floor, these pixels have intensity close to 0. These are the pixels which you see in this, the coat that is that this cameraman is wearing. If you observe carefully, this three-dimensional picture, if you observe carefully, if you compare these two images, that's why I converted this into an isometric view. If you compare these two images, you will see that this arm of the cameraman is visible to us over here. The coat of the cameraman is visible to us over here. The camera itself is visible to us as these spikes. The face of the cameraman is visible to us as these spikes, and so on and so forth. So what you saw in two-dimensional grayscale image, in three-dimensional, it appears like this, and this is a very complex function. The reason why we call it a function is, in mathematically, a function connects two things, the output to the input. The output in this case is pixel intensity. The input is the position, the x1, x2, the position of the pixel in the picture. So this 3D surface, if you observe carefully again, what you notice is all those positions in the original image where the pixel intensities change abruptly, suddenly. In those positions, you'll see an edge. Up till this point, all these pixels belong to the sky. But after this point, the pixel intensity suddenly dropped, and this forms the edge. This edge important to us? What do we do with this edge? Let's see that. So to understand the process of convolution, you need to look at all the images as 3D images, where the third dimension is pixel intensity. If you're able to get this in place, this particular way of looking at the image in place, then convolution becomes pretty easy to understand. So let's go ahead and see what this convolution is all about. Can you read the line written after the arrow? There is a line written over there, but I'm sure you're not able to read it. And the reason why you're not able to read that is, for us to be able to see any object, that object has to have a different pixel intensity compared to the background. I have a very beautiful video here. I hope you'll be able to watch this video on the net. Let's see this video. Look at this video. I repeat, the octopus, which was camouflaged, was not visible to us until we approach it very close. Now it becomes visible to us because it has acquired different pixel intensities and pixel values than the background. So I'm going to leave this URL to you. Please go ahead and enjoy this URL, a very beautiful URL. And sorry about that. Coming back to this. These edges that we detected, that we just now saw on the three-dimensional picture, these edges are what we need to extract using convolution neural network. I'm so sorry. I'll be back with you in a second. I switched off my presentation. That's okay. Apologies, and I'm going to share the screen now. All right. Okay. Unfortunately, I don't see where the share screen is. Okay. I wonder if you're able to see the screen, the presentation. Okay, I'm assuming that you're able to see the screen. People in the technical support need to tell me, are you able to see the screen, please? Okay, and I'm assuming that the screen is back. I'm going to move on. So we saw this image as three-dimensional function, and we also noticed that what defines the cameraman, the boundary of the cameraman, is available to us as the edge in the three-dimensional image of the same cameraman. So let's see how we can exploit this in convolution. And coming to this point, what I was trying to tell you here is, for us to be able to see any object, that object needs to have a different pixel intensity than the background. Only then you will be able to see the object. For example, in this third bullet, I'm sure many of you will be able to see there's a line written over there. Can you read this? Even though the font is white, the font which I have used is white, and the background is also white, the whiteness is not the same. Hence, you're able to see the line. So what I'm trying to draw your attention to is, to be able to see any object, that object has to have a different pixel intensity values than the background. And due to this difference, the object of interest, the foreground object, it gets a distinct boundary. That boundary defines that object. You might see a boundary inside a boundary. For example, if you're looking at a cat's face, you might see the cat's eyes, the cat's nose, and all forming different boundaries. It is the shape and the orientation of these boundaries that define the object. And these boundaries are made of edges. And edges are formed by the sudden pixel intensity changes. For example, this image which I'm showing you of a cat here, cat face. I'm sorry, I shouldn't have told you that it's a cat face. I want you to guess what is this image about. This image is definitely about a cat, but a horse. It's not nothing, but it has to be a cat, right? And what defines is the different boundaries of the various features that go into making of the cat. The whiskers, the nose, the eyes, the position of the eyes and the nose, the whiskers, so on and so forth. So let me summarize what I've been telling you till now. We look for these kind of edges. These edges define the boundaries, and these boundaries put together define the object. And to detect these edges, we need to be able to find out in the original image, the two-dimensional input image, if I'm working with grayscale, two-dimensional input image, where all in that image does the pixel intensity change drastically. Wherever the pixel intensities change drastically, that indicates presence of a potential probability of a feature of that particular object. Why do I say potential? Why do I use the word probability? We'll see that next. When you're looking for these kind of edges, by looking for difference in pixel intensities in the images, unfortunately, life is not so easy because we have a concept called digital noise. Whenever we use any digital camera, whatever brand, whatever quality it might be, these digital devices themselves can introduce noise into the picture, where noise in a digital picture is unwanted changes in the pixel intensities. Changes in pixel intensities caused not by the real edges that define an object, but by other factors that come into play when you're doing that sampling and quantization, the digital quantization, amplitude quantization, which I mentioned earlier. When you take a camera and you click a picture, there are various sources of noise. There are various reasons why the pixel intensities can be something other than what they should be. One of them is called the photon noise. This is due to the quantum nature of the light itself. The other one is the thermal noise. This is caused because of the heat generated by the digital device that you're using. That's why many times people who come from the background in astronomy would have observed that when you're clicking a night sky image, those cameras are super cool before taking the picture. Sometimes these digital noise are also caused by the hardware, the chip-related reasons. So there are various ways in which noise can creep into the picture, the digital image, and that can lead to unwanted fluctuations in the pixel intensities. For example, in this case, this is a digital image of a water body. And when this image was clicked, the reason why the pixel intensities changed in this area is because of the shadow of the trees. But the reason why pixel intensities change here, where there was no shadow, the water was still, the sunlight was at its peak, but still we see slight changes in the pixel intensities there. Those pixel intensities probably are caused by digital noise, the unwanted fluctuations in pixel intensities. Why should we worry about digital noise? How does it matter? Convolutional neural network works at pixel levels. At pixel level, it goes and looks for changes in pixel intensities. And if we leave the digital images with these noise, then convolutional neural network will absorb this noise, consider these changes in pixel intensities as features, as edges which define the object, though they are not really the edges that define the object. Hence, in digital image processing, especially using CNN, one very important task that we do is we try to remove the noise in the digital image as a part of pre-processing the images. Otherwise, the CNN algorithm can misinterpret them as true edges. There are various ways of removing the noise in the digital images. One very popular technique is called Gaussian blurring. I'll just quickly show you what Gaussian blurring looks like, but we'll not go into the details of it. I'll leave it for some other session. This is the digital image of a very famous picture called Lena, an image which is often used in digital image sessions. If I compare these two images, for us, human eye, this digital image is much more clearer, much more sharper, it has much more information. However, this image is not suitable for convolutional neural networks. Why? If you observe carefully, look at the eye. We see a lot of pixel intensity fluctuations in the eye. What are the reasons for this? We don't know. If CNN, convolutional neural network, works at pixel level, it's going to consider these different changes in pixel intensities as edges that define the eye, which is not correct. So we blur this image using a concept called Gaussian blurring, and the result of that is this image. What you see here in this image, it looks very blurred, not very comfortable to look at. But this is the image which CNN will be happy to work on. In this image, it will be able to find out the true features that define this person. Whereas if I input this image, very likely that the CNN will end up absorbing a lot of unwanted pixel intensity fluctuations as the features that define this person. This is a very famous URL. I'm going to leave it to all of you. Please go and explore this. How noise can bring down a well-trained convolutional neural network. What we see on the left is a panda. The well-trained CNN is 57.7% confident that it is panda, and it's doing a correct classification. To this digital image, we can add amount of noise, digital noise, 0.007 into a digital noise. This digital noise obviously is shown as a picture here, but it will be shown actually be a grid of numbers. That grid of numbers is added to this grid of numbers. The result of that is this image. To you and me, this image also looks like a panda. We see no difference between the left side image and the right side image. However, the same CNN, which is earlier 57.7% confident that it's a panda, now it's 99.3% confident it's a gibbon. And the reason for that is the noise that we have introduced into the digital image. So in CNN, when you're looking for those edges using the process of convolution, we have to make sure that the unwanted edges caused by the digital noise are erased as much as possible. So what we have discussed till now is a digital image as a three-dimensional function. When you look at a digital image as a three-dimensional function, you see the features or the features that define the object appear as edges in the three-dimensional image. And convolution is the process of looking for these edges in the input image. So let's go and see what convolution is. Once again, I'll first take the approach which you often come across in books and articles. Convolution is often defined as two functions interacting with each other to give a third function. A very common example of this will be if any of you have used what you call, I think it's called the karaoke. I may be wrong. I think that's what it's called, karaoke, where you sing along with the background music and your voice gets merged with the background music. So the background music is the original music. Your voice is this. Both of them interact, and the output is you singing the song with the supporting background music. In our world, in convolutional neural network for image processing, the original image is a function. We have already seen that. We will use another function, which I have not yet discussed with you. This function will interact with this function, and in the process, it will tell you where all in this original function, where all, at what positions are the edges available. Those edges, those positions where the edges are available, that will be given to you as what we call the feature map. As the name suggests, feature map, map of or position of the features that were extracted by this convolution process by using this function and making it interact with this function, where you can think of this function, original image, as a three-dimensional function. And what is this filter? We'll see that now. We'll see that soon. So the process of using a function on the original image function, and in the process extracting the positions where the edges are, that process is called convolution. Once we understand this concept, the mathematical formula that is often used to explain convolution will become easy for understanding, will become easy to understand. Now, I'm not going to go to mathematics right now. I hope you get an idea of what convolution is. So once again, I bring back the three-dimensional picture. On this three-dimensional picture, I'm going to run, this is what we call a kernel. Some people call it filter. It's often, the two words are often misused or used one for the other. Ideally, this should be called a kernel. A set of kernels is filter, but we ignore that detail. Let's call this a filter. What this filter consists of is basically two values in this case. In this example, only two values, -1, +1. So when I put it on this position, what's going to happen is -1 will be multiplied with one pixel value. This one will be multiplied with the subsequent pixel value, two neighboring pixel values, and these two products will be summed up. So suppose the first pixel value is say 100, the next pixel value is say 50, 100 into -1 is -100, 50 into 1 is 50, add these two numbers. When you add these two numbers, you'll get -50 as output in this example. So these two numbers will be multiplied by all pixels and the corresponding neighboring pixels. The product will be added together, and the difference is what will tell you how two neighboring pixels differ in terms of. This is equivalent called dy by dx, find the derivative or the gradient. What we're trying to find out is when I change the position of a pixel from one unit, imagine this is pixel 1 and this is pixel 2. When I move from this position, pixel 1 to pixel 2, what is the change in pixel intensities? How much it changes the pixel intensities? Suppose this is pixel 1, position 1, this is position 2. Both the pixel intensities are almost same. Hence, when I run this -1 +1 on these two pixels, the neighboring pixels with same pixel intensities, the output will be a 0. So I repeat this animation. As this function spans this original function vertically, that's what we see happening here. Since the pixel intensities in these regions are almost same, the difference in pixel intensity will be very close to zero. May not be exactly zero, but very close to zero. But when it comes to the edge, this part, when this function comes to this part of the original image, at this part, it finds a significant drop in pixel intensities that is indicated by this arrow. And that tells you that at this position, there is a very huge change in pixel intensities, the magnitude of pixel intensity. In other words, this indicates to you possibly an edge, the presence of an edge. So when you scan this image top to bottom, and then horizontally, left to right, this function will be able to extract all the positions in the original image where there is a sudden change in pixel intensities. In other words, you will end up discovering this boundary, these edges, which defines the cameraman. I've given all the same points in bullets. So in case you want to revisit these bullets, please do. This process of using a function which scans the given function and looks for the sudden change in pixel intensities and extracts those positions where the sudden changes happen. This process is called convolution process. Okay. So what I've shown you here is an example. Usually the function that we use is not the function that we use to scan the image is not as simple as -1 + 1. It's not. It is slightly more complex than that. But I hope you got the idea of what is convolution. Okay. Sorry. Oh my God, looks like screen sharing is not on. One second, please. Okay. Unfortunately, I don't see any option for sharing screen on this live stream. Maybe I should check this out. No, this is not the one. Yeah. Okay. I'm awfully sorry. There was something hiding behind this. What is there on the screen? I'm going to repeat this, whatever I said. I'll just take a few minutes and repeat whatever I said. Yeah. I think I lost the screen somewhere here after the video. So I'll quickly tell you whatever I showed, wanted you to see here. This is where I think we lost the screen. So what I was trying to tell you here is, for us to be able to identify objects in an image, it's important that the object's pixel intensities are different from the pixel intensities of the background. When you do that, the process of convolution will be able to extract boundaries that define the object. Before we go into convolution process, one thing that we need to also understand is the digital noise. Basically, digital noise is the unwanted pixel intensity fluctuations caused by various factors that come into play when you're doing the amplitude quantization, basically sampling. One of the sources of the noise is the nature of light itself, which is basically quantum physics. I will not get into that right now. The other problem with the other reason for this noise is the thermal noise caused by heating up of the device which you're using to capture the picture. And sometimes the electronic components themselves, they cause digital noise. And as a result of digital noise, what happens is the pixel intensities, they change. They are something more other than what they're supposed to be. I can understand the pixel intensity changes in this region because of the shadow. This is a picture, a very close-up of a water body. What you're seeing here is the shadow of the trees. Whereas this part, though the water was almost still, sun was bright, still in this part, we see some fluctuations in pixel intensities. What causes these pixel intensities? We don't know. Could be any of the reasons listed below. Probably these are the digital noise. Why is digital noise a problem? Convolutional neural network works at pixel level. At pixel level, it extracts the positions of all those pixels where there is a change in pixel intensities. And if we don't do something about this noise, convolutional neural network is going to think that these pixel intensity changes, which are actually caused by digital noise, are also part of the features that define the object. That's why we need to remove the digital noise. And to remove the digital noise, we use various techniques. One of the most common technique is what is called the Gaussian blurring. It acts like an eraser. Once again, I'm not going to go into the details of this. This is a famous picture of a person called Lena, often used for digital image sessions. I've compared two pictures here. Don't worry about the color. This is grayscale, this is green scale. Let's not worry about the color part. But of these two pictures, the one on the left looks more clear to us. One on the right is very blurry. But this picture on the left, which is more clear to us, has more digital noise. If you zoom into the eye of the person, there is a lot of pixel intensity fluctuations. These pixel intensity fluctuations don't define this person. They don't define the eye of this person. What causes these pixel intensity fluctuations? We don't know. Many reasons. So what we do is, this image is denoised by using a Gaussian filter, and the output of the Gaussian denoising looks like this. Hopefully, by transforming this image to this image, we would have probably gotten rid of many of these unwanted pixel intensity changes and retained the true pixel intensity changes which define that object. So when you're working on digital images using CNN, it's very important that we do something about the noise. A very beautiful article, some of you might have already read this. Those who have not, please go and read this. We have an image of a panda, which is a digital image. The CNN, which is trained to identify these, classify these different images, the CNN model is also confident 57.7%, it's greater than 50%. So it's also classifying this as a panda. To this image, we add noise, a fraction of a noise. Okay? This noise, which you see here as an image, is basically a set of random numbers. You should imagine this matrix to be a set of random numbers. And this image on the left of the panda, which you see here, is also an array of numbers, pixel intensities. So what we do here is, we insert some noise into this image. The result of that is this. To the human eye, there is no difference between these two images. Look at it as closely as you wish to. You won't see any difference. But when you run the same CNN model on this, it is 99.38% confident that this is a gibbon. Why did this happen? This happened because this noise introduced into this image sudden pixel intensity changes caused by digital noise. Intensity changes that don't define the object. And the well-trained CNN model is completely misled into classifying this as a gibbon. Please read this article, and it's a very beautiful, it gives a very beautiful insight into why the digital noise can become a headache when you're doing the convolution. So now let's understand what convolution process is. At this point, we are seeing digital image as a function. We understood convolution is the process of running a function against the image function to identify where all in the original image there is a sudden change in pixel intensities. At those positions, you probably have an edge which defines the boundary of the object. So let's look at convolution process slightly in more detail. When you read about this, you'll often come across this image where you're shown an original function interacting with another function, which is called a transformer. And the result of that is a new function. The example which I often quote in this case is, as I said, the concept of karaoke. I think it's called karaoke. I don't know what it's called, where you sing into the mic and your voice is reproduced on the speakers along with the background music. So it looks like as if you are standing and singing with the background music playing around you. So you have your original voice, you have the background music, both of them are mixed together and you get a perfect music as output. In the world of CNN, convolutional neural network for image processing, the original image is one of the functions. Then we'll use another image, which is often called filter or kernel. These two words are interchanged. The filters is supposed to be a combination of kernels. I'm going to call it a filter. So we have the original image, and we'll use another function called filter. And by making these two interact with each other, the result of that will be an output which is called a feature map. As the name suggests, feature map is a map. It basically tells you the positions in the original image where there is an edge, which probably belongs to the boundary that of the object in the foreground. Slightly in more detail. So this is the same three-dimensional function. So this is my original function. On this function, I'm going to interact another function. Another function is going to run on this function. It's going to interact with this function. This process of interaction is called convolution. And in the process of doing so, it's going to extract these edges that define this cameraman. How does it find out these edges? It multiplies. If you look at this filter, it has two numbers. The pixel with -1 and the next neighboring pixel with 1. Whatever the pixel value, suppose the pixel value of this pixel is say 50. -1 into 50 is -50. The next pixel intensity is around say 100. 100 into 1 is 100. You total up these two values, you'll get the difference in the two pixel intensities. So let me show this in animation to you. So this filter is convolving right now with this original image and generating the feature map for you. The feature map will actually not look like this, but for the sake of simplicity, I've shown it like this. I repeat this animation again. The filter scans the image, and wherever the pixel intensities of two neighboring pixels are not too different from each other, the result of this convolution will be very close to 0. Wherever the pixel intensities of two neighboring pixels, they change abruptly, suddenly, the magnitude of the difference will be a very large number. This number can be a very large positive number or a negative number. So in all those positions where there is a sudden change in pixel intensities, either it's negative or positive, doesn't matter. Those are the positions where there is a potential edge. Why do I call it a potential edge? The reason why I call it a potential edge is because it might even be caused by noise. Right? So this process of using a filter to scan an original image function, and in the process finding out the positions where the intensities change drastically, this process is called convolution. Of course, the filter which I've shown you here is not as simple as this. This is just for example. But whatever filters that you probably have come across already, those filters, the 3x3 matrix or 5x5 matrix that we generally use, their function is also the same. They scan the original image, And in the original image, they give you the positions where there are likely to be boundaries or edges. And this process is called convolution. And these edges that we're looking for, they appear as gradients. Gradient is nothing but dy by dx. That is how the y changes, how pixel intensity changes when I change one step, pixel by one step. So in this region, when I change pixel by one step, I move from one pixel to next pixel, there is no change in pixel intensity. So dy by dx will be close to 0. But when I come to this region, where one pixel is close to 200, but the immediate next pixel is gone to 0, there dy by dx, change in pixel intensity, for 1 unit change in pixel position, dy by dx will be a very large number. It can be a large negative number, or it can be a large positive number. And these large negative or positive numbers indicate potential edges. So let me show you the same thing on another image. This is image of a cat, a grayscale image. The result of this scanning, this grayscale image, we scanned it vertically. The result of this scanning will be horizontal edges. All these eyebrows, all these the boundaries that define the eye, those things will appear sharply here as features. But the the vertical edges defining the nose, that will not come out cleanly. Why? Because you're scanning top to bottom, vertically. So when you scan vertically, you'll get horizontal edges. When you scan horizontally, you'll get vertical edges. So we need to scan in both the directions. So when I make use of this filter and scan on the original image in both the directions, that's when I end up detecting these edges. And once again, this image that you see here is only for explanation. The output doesn't actually look like this. It is basically a set of numbers. And this is what is called the feature map. So again, the same thing I've explained here in slightly more detail. What happens when you run that -1, that filter on this image. I've taken some pixel values examples and explained the same thing to you. So in short, whenever you run a filter on an image, what you're essentially doing is finding out how the pixel intensities change with every one unit change in the pixel position, both in the vertical direction and in the horizontal direction. And mathematically, this is equivalent of finding dy by dx, that is a gradients, which will help you find the edges. Some of you who come from mathematical background may find this strange, because for finding the gradient using dy by dx, we need a continuous function, mathematically a continuous function. Whereas images are not continuous function, they're discrete functions. That's absolutely fine. We can still go ahead and use the approximation. If you want to know further about this, please look at what is called the discrete calculus and the Taylor series approximation techniques. I'm not going to get into all those things right now. We don't need them here to understand the concept. I hope with this discussion you understood what convolution as a concept is. Once again, I repeat, this filter which I've used here of -1, 1, this filter is only for example. The filters are usually more complex than this. They are generally 3 by 3 or 5 by 5 matrices, where the values inside those filters are learned through backpropagation in the CNN. Once again, it's a topic for discussion reserved for some other time. Right now, I'm going to move on. So now I hope whenever you see this kind of an explanation of convolution, you will quickly understand what's going on. This grid represents your original image, and the values in this grid represent the pixel intensities. This grid represents the filter, and the values are fixed in such a way through the backpropagation of the CNN. The values are fixed in such a way that when you scan this filter or this kernel on this image, the result of that is the feature map, where the feature map actually tells you in what positions of the original image do we have a gradient and what is the strength of those gradients. That is what this feature map is. I hope now, after this discussion, you'll be able to understand this particular way of explaining convolution. So this is the same cameraman on which I have used what is called SOBEL, Sobel filter, a very popular and very famous filter that used to be used before CNN was developed. But these days, it's not used. Still, you can go ahead and try this out on this cameraman. So when you run it horizontally, you detect vertical features. When you run it vertically up and down, you detect horizontal features. Combining these two feature maps gives you this. So finally, what defines this cameraman and the camera is the edges. Same way in Lena. If you look at the Lena, when you scan it horizontally, you detect the vertical edges. And when you go vertically, you detect the horizontal edges. Combine these two, the resultant feature map is this. And what defines Lena as a person is these edges. So now the CNN, convolutional neural network model, whenever it sees these kind of edges with these kind of orientations with respect to each other, it will identify that as a Lena. On the other hand, whenever it sees these kind of features with these kind of orientations, it will identify that image as a cameraman. With that, I hope you understood the concept of pooling. With that, I'll take you to another concept called, with that, I hope you understood the concept of convolution. And I'm going to take you to another concept called pooling. Contemporary neural network models that have come across, the latest ones, generally they don't use pooling. I'm talking about the various famous architectures such as ResNet or Inception modules from Google. These don't make use of pooling much, and many other people have stopped using pooling, but still, because it's an integral part of convolutional neural network, I think we should spend some time on pooling. Once again, when you read about pooling, you'll come across these kind of images where you'll be shown a grid of numbers with 4 quadrants. And then if you're using a technique called max pool, what will be told is, since 140 is the largest of these, 90 is the largest, 240 is largest, 250 is largest, pick them up and put them over here. You have another technique called average pooling. If you use average pooling, average of all these 4 numbers will be put over here, average of all these 4 numbers will be shown here, so on and so forth. A very beautiful discussion on pooling is available at this URL. In case you have time, please go through this URL where you'll see this image with the explanation. However, as I said earlier, this also leaves the students with a lot of questions. What is this? I've already given to you on the top. This is the output of the convolution process, and it is called the feature map. The feature map has, at various positions, the magnitude of change in pixel intensities. All the magnitudes are shown here in positive. May not be. They can be negative as well. And out of this, we are extracting the max values. Why are we doing this? What is the reason for extracting only 140, 90, 240? Why not the others? So that's what I want to bring out here as conceptually. I came across this particular image on LinkedIn. So I thought this would be a good way of explaining pooling. You have image of a dog. It's a grayscale image. You can cut these images into vertical stripes and rearrange the stripes, and you get back the same dog. But this time you get 2 of them. Once again, I can horizontally cut them into pieces and rearrange the pieces, and we get almost 4 dogs, not exactly 4, but almost 4. So what this is telling us is, in the original image, And in this image, which we see here, the fourth step, we can still identify this object is a dog. That means there are a lot of pixels in this image which are redundant. We don't need them to define this dog. And if you have followed the convolution concept, you will agree with that what defines this dog is the edge. All those pixels which you find here, or all those pixels that you find in the neck or the forehead of the dog, all these pixels, not all of them are equally important. Not all of them are required to define this dog. So many of the pixels are redundant. And the same thing happens when you generate feature maps as output of convolution. Many of the gradients given the feature maps are redundant. Those gradients, they don't define the object that interests us. So we have to remove that redundancy, and that is what is done using pooling. So let's look at pooling. What you're seeing here is a digital image now not being shown as a set of pixels with pixel intensities. But what we would like to look at this digital image as is, at every pixel position, what is the magnitude of change in intensity? So I've shown you only two examples here. If I look at this red pixel, a pixel under the red box, what is the change in pixel intensity and which direction the change is? So I'm looking in this example, I'm taking example of max pooling. You can imagine that max pooling. In which direction, if I stand on this pixel, in which direction is the pixel with largest intensity compared to itself? So I can transform this entire digital image from a set of pixel intensities into a set of pixels. When you do that, now your entire digital image, at every pixel position, you have very small tiny arrows, may not be visible to you from your side, but there are very minute arrows over here indicating how much the pixel intensity is changing in its neighborhood and the direction of the change, whether it's increasing or decreasing. And if you observe, not all pixels have very strong pixel gradients. Those which don't have very strong pixel gradients are generally the ones which are redundant, useless. They don't define the features of the object. So what we do here is, on the output of this, the convolution layer, which is called the feature map, we again place a small window usually a window of 2 by 2, and try to understand within that window of 2 by 2, what is the general direction of those gradients. So instead of looking at the image as a pixel with gradients around the pixels, this is information overload. So gradient of every single pixel will be too detailed, too much of information overload. So instead of that, can we capture a general trend in the flow of gradients in every region of this picture? That region is defined by a 2 by 2 matrix, usually 2 by 2 with a stride of 2. If you people have already used convolutional neural network, you know what I'm talking about. In case not, don't worry. So on this feature map, we place a grid of 2 by 2. And within the 2 by 2 grid, what is the average direction of the gradients? Or what is the maximum gradient direction? We look for these two different things, either maximum or average. When we do that, the result of that is, this is what I wanted to show you. When you do that, the result of that would probably be a feature map like this. And if you look at this feature map closely, you'll see the eyes of the person, the nose, nostrils, and the lips is visible here. These are the ear, and you might even see the hair of the person. Once again, I repeat, the output of the convolution is a feature map. feature map is basically at every pixel position, what is the gradient? If you look at every pixel position, what is the gradient? It's an information overload because not all pixels have strong gradients defining the features. So we have to somehow extract only those useful pixel positions where there are strong gradients and ignore the others. That concept is called pooling. And to do that, we make use of a grid. Usually this grid is of the size 2 by 2. And within this 2 by 2 region, we try to understand what is the general trend of the gradients or which one is the maximum gradient. And we generate the output of the pooling. From the pooling, you get an output. The result of that is this. So pooling is also called subsampling. What you're essentially doing is, which is a feature map, you're subsampling and extracting only those positions where there are strong gradients. And when you look at those together, you end up seeing the object. Basically, you end up seeing the edges that define the object. But this won't happen in the first few layers of convolutional neural network. Usually, you'll start seeing this kind of macroscopic features in the innermost layers or the last few layers of the convolutional neural network. The first few layers of convolutional neural network will always extract what is called the Gabor, G-A-B-O-R, Gabor features, which are basically atomic level features. And they're nothing more than vertical lines, horizontal lines, angular lines, so on and so forth. As you go down into the CNN, convolutional neural network, and at every stage that you go down, the features are pooled together and the redundant pixels are left out. What you end up in the last few layers is the macroscopic features that define the object. And of course, all these things which I'm showing you here right now, please understand that this is all the output of a library such as matplotlib library. But what you will actually get is a bunch of numbers. So it will be a grid of numbers. Those grid of numbers, if you pass them to the matplotlib library, you'll see an image like this. Okay. So with this, I hope now you'll be able to understand when you come across images like this explaining pooling layer, what's happening here. So what's happening here is on the output of the convolutional layer, which is a feature map, a max pool has been applied. What the max pool does is it looks for in that region, the 2 by 2 region, in which direction and what is the magnitude of the maximum gradient. That has been picked over here and put over here as the output. So from every region of this feature map, it's extracting in this example what is called the maximum gradients available in those regions. That's why it's called max pool. If you go for average pool will, for this region, will be average of all these 4 numbers. And generally, average pool is avoided. Average pooling is avoided. The reason for that is, don't forget, the feature map, it shows you the gradients at different pixel positions. But these gradients, especially the smaller ones, might have been caused by digital noise. So now if I use average pooling technique, average pooling, you will average the digital noise also into your information. But we don't want to capture the noise into our information. So to avoid absorbing the noise into your subsequent analysis, go for max pooling. The larger the gradients, very unlikely that these are caused by those digital noise. But if you're not careful, larger gradients can also be caused by noise. Imagine you are building a CNN model to identify faces, and some of the sample pictures that you have with you, those sample pictures were taken, unfortunately, in a position where you have a shadow following on the face of the person. Now, when a shadow falls on the face of the person, the boundary of the shadow will create sharp gradients in the convolution process. But those gradients don't define the person. So you have introduced noise there. Usually, these kind of unwanted gradients, which are caused by these kind of things, such as shadow, these things cancel each other out when you have many data points to train your model on. But the digital noise caused by the various other factors which I mentioned, they cannot be eliminated. They can never be made zero. They will always be there. So hopefully through Gaussian filtering process and all these things, we will be able to reduce the noise, digital noise, to such an extent that convolution extracts only the true features. And when you use pooling, if you use pooling, go for max pooling, because that way you will avoid the chances of absorbing noise into your further analysis. All right, with this, I'm going to stop here. And the deck which I've shared with you has subsequent slides as well, where I've tried to explain to you what exactly happens when you take a digital picture through your device and how that process introduces noise into the digital image. But I'm going to leave this detail to you. A very beautiful URL from where I actually understood these concepts. You can actually go through these URLs, and you can also understand these concepts of how digital images are created and what are the different reasons where noise can creep into digital images. With that, I'm going to stop here. And I hope you understood the concept of convolution pooling. Feel free to ask any questions. Sincere and true apologies. I did not realize that the screen sharing was not working until it was pointed out to me on the chat. I hope with that mistake, you're still able to understand what convolution is and what pooling is. Feel free to ask any questions if you have. Okay. This is to my technical team. I hope you're able to hear me. And if any questions, please kindly forward it to me. All right. In that case, since I don't see any questions on the WhatsApp, and I hope, again, this is not a connection issue, I think I'm going to stop here. And once again, my sincere apologies for the screen suddenly going blank. Hope to meet you all again sometime very soon. And take care. Bye-bye.